Bin-Yu is a distinguished Chancellor's Professor in the Department of Statistics and ECS at UC Berkeley. She chaired the Statistics Department at Berkeley from 2009 to 2012 and was president of IMS from 2013 to 2014. She received numerous honors, including being inducted into the National Academy of Sciences and is a fellow of the American Academy of Arts and Sciences. Bin's research focuses on statistical machine learning and causal inference, with interdisciplinary research in neuroscience, genomics, and precision medicine. We are honored to have Bin present this year's Breiman's Lecture, and the Breiman Lecture was introduced in 2015 to highlight work in statistics relevant to the conference topics. And apt to giving this lecture, Bin actually now occupies Leo Breiman's old office at Berkeley. So I'm looking forward to her talk on vertical data science.
Thank you very much for the very kind introduction by the organizing committee, and truly an honor for me to speak here, especially under the Breiman Lecture. So I'm part of UC Berkeley Statistics and ECS. I'm also part of the Berkeley Lab and also the Charles Zuckerberg BioHub as an investigator. So for some of you like me, when my friend Tian Zheng from Columbia suggested a new title for my paper, which you see that the old title was Three Principles of Data Science, I had to look it up. So Veridical means truthful and coinciding with reality. So I think it's quite fitting. Since this is a Breiman Lecture, I just want to share some photos about Leo, who was truly ahead of his time, a data scientist, and also a modern-day polymath. We know his work from statistics and machine learning well. He was also a sculptor. He also traveled widely and author of 3 books. And actually, I have a painting, the last one, on my wall when I occupy his office. So he was just really original. I think many of you might not remember 2001. So what happened? 2001 was the first Harry Potter movie. And I think a lot of you are pretty young, so probably don't remember watching that. That's a good thing. I wish I'm young. The same year, Leo Breiman published 2 very important papers for him and for the community. The first was statistical modeling, the 2 cultures, basically contradicting the statistical culture, generative models, with the machine learning culture he called accuracy modeling culture, which you have algorithm and you have kind of black box and you just do prediction. And the same year, his random forest paper was also published. So my talk will actually have connections with both papers, as you'll see. Fast forwarding 2019, this year, AI is all the talk, right? We can debate what's the real definition of AI, but beyond this community, people just talk about AI. And Bill Gates said AI is like nuclear energy, both promising and dangerous. For the mission-critical applications such as criminology, self-driving cars, precision medicine, right? The dangers really have to be hedged or mitigated so that we have safe AI out there. My background or my work is mostly coming from recently biomedical problems, and they're pressing. And data science is a key element of AI, because AI, as we know now, is very much data-driven and big data-driven, and data science integrates computer science, stats, and machine learning, and domain knowledge, and a very active interface between computer science and statistics, where Leo Breiman really championed with machine learning at the interface. So I'd like us to see the whole data science lifecycle as a whole system, not just disconnected parts. We start from domain problem question. We do data collection, data cleaning, which takes usually 80% of our time, which we don't talk a lot, and data exploration, and the typical modeling and algorithm, which most of the talks in most conferences is on the modeling phase, which is very important, but it's only one step in this whole system. And then we have post-hoc analysis, interpretation, and go back to the domain problem. A huge not discuss topics the human judgment call in the entire process. We make so many calls in how we do the different steps. Veridical science is really trying to extract reliable and reproducible information from data with an enriched technical language. I think we really need to describe what we do to the people outside much better with something more accessible and basically boring persuasive arguing or debates from liberal arts to really help us communicate the evidence in the context of human decisions and domain knowledge. So for the rest of the talk, I will describe the Pca Framework, the 3 principles of data science. Actually, I've been giving the talk. It's a whole evolution process with a lot of help from the community to form the final paper, which we call Veridical Data Science. It's really trying to connect machine learning with statistics. And then a particular case is really building on Leo's work on random forest to add even more stability to random forest, and then make it interpretable for genomic problem and beyond. My motivation to go down the PCS route was actually interpretation. Starting with predictive models with LaSue, I wanted to interpret the model so that we can do follow-up experiments with Jack Galan's lab. So that's really behind all this motivation by interpretation. How can we evaluate and select different interpretive methods for the goal and come back to do more science and more domain problems? And for that, we also have a general methodology called agglomerative contextual decomposition, which for general deep learning interpretation. So the Pca Framework is really a step towards veridical data science. As I said, this is a work trying to build on machine learning, bringing statistical considerations, and the paper is in the final stage of PNS with my former student, Kumbir. So the 3 principles, the first is take predictability. Statistics always had predictability, but it was not at the center. Statistics had other things seem to have got more attention. Computability is underlying all what we do from storage, calculation, and scaling up algorithms. But we also add, as I will say later, about serious compute simulation. I want to bring in a lot of consideration from statistics to machine learning and integrate to come together and to build a veridical data science tree, which is rooted in stability, use computability as a trunk to support, and have fruits like predictability and interval results. It really bridges Bryman's 2 cultures. PCS also connects where I come from, a lot of scientific collaborations. It really connects science with engineering. I see data science, both science and engineering. Predictability and stability really embed 2 very important principles from science, predictability and replicability. And computability, I want to expand from the traditional to include serious simulations as happening in computational chemistry, computational biophysics. We take our simulations as another means to understand our algorithms and to push the field forward. But we need to have a lot of data and subject knowledge into the simulation models than just always take Gaussian in the simulation. I started working on stability through predictability in a project with Galan's lab to do movie reconstruction. And we want to integrate the models. The last step was LaSue. It was kind of Gabor and then LaSue. And it attempts to unify the existing works of different versions of perturbation analysis, bootstrap, sensitivity analysis, and different models in robust statistics. Interpretability, reproducibility were very much on my mind, and then in recent time we moved into causal inference and use PCS, especially adding stability to machine learning, to really do hypothesis generation and for knockout experiments. So stability is really, I'm seeing the system as a system, you're shaking the system so that it doesn't break. The shakes, a lot of come from the human judgment calls. Why do you do bootstrap instead of subsampling? Why you do cross-validation and random split? All these questions we usually do 1 or 2, and data cleaning in genomics, there are standard ways, more than 1, to clean, say, RNA-seq data. Why don't you do both? And would you get different results? So all these questions I want to bring to the forefront so that we can discuss and debate, and the users, our outcome, will actually know we did all these judgment calls and either agree with us or not agree with us through documentation. So just make the process transparent. Many of us know, but even we don't even remember what judgment calls we made. So to make that reproducible for the next person and for the users of our results. So the PCS workflow is try to really take into account 3 considerations PCS in the whole data science lifecycle. So it's clear that for modeling stage, predictability is a good way to check reality. But even when you do problem formulation, future is always, should be in your mind. So in this sense, P is always there. It's about the future. You never do a problem just because you have nothing to do today and you finish. There's always something to follow up. New patients, new users, new platform, new collaborators. So all these things should be in your mind when you formulate a problem. And stability is even relevant for the modeling formulation stage or the problem formulation stage in the sense that terminologies change. When I was a graduate student, ML used to mean maximum likelihood. Right? LDA was linear discriminant analysis. All the things change. And matrix in cancer biology means something very different from what we mean. So if we work with a cancer expert, we have to really clarify the meaning of this English word. So there's something called linguistic stability, people studying linguistics, that is a consideration for us because we have multidisciplinary teams, and terms mean different things. And data cleaning is an under-considered or under-reported step. So let's look at the perturbation. Oh, before that, we also expand statistical inference to our PCS inference for perturbation intervals, not just about the modeling stage, taking into account problem formulation. If you want to see whether a particular gene or particular feature is important, would you get the same result if you go through lasso, go through random forest, or go through deep learning? So all these stabilities can be considered under the perturbation intervals. So the perturbations we're familiar with under roughly symmetric and weakly dependent assumptions, they are there, so we try to unify them. But the recent perturbations are different model modalities. You have different type of data to answer your question. That's also a choice. It's also a perturbation to what you're going to use. And also synthetic data. You can also do PDE-driven, have synthetic data together with data to model. That's a form of perturbation considered under PCS. And under different environment, that can be done for causal inference, called invariance. And differential privacy, US Census already decided to do differential privacy form of stability as well. And in this community, probably mostly the adversarial attacks to deep learning algorithms. You can easily flip diagnosis of medical images by pretty minor perturbations. And this is disconcerting. The database can be attacked. There was an article a couple of months ago, people worried about whether this imaging database can be attacked. Say, insurance want to gain by changing the labeling in certain ways. It's not just about self-driving cars. These medical images can also be attacked. So how can we mitigate these dangers? And another form of data perturbation is data cleaning. I don't know how many are aware that this paper by Reinhardt and Rogoff, 2 professors from Harvard, have been critiqued in the literature. It was a 2010 paper in American Economic Review called Growth in a Time Debt. And this paper has been cited in popular press as evidence to say that high debt and GDP ratio is bad for growth, and has been used to support the austerity policies both in UK and in the US. But if you look deeper, which people did, you really should call this a very important decision, very important work. We need replication, just like in science. 2014, 3 economists from Amherst tried to replicate the result. And they discovered that the original author did some exclusive data cleaning. They excluded some data from New Zealand, and also some coding errors, and unconventional weighting. And when they did bring the data in, the conclusion reversed, mostly. So this just says it's just one step, a few data points can really change economic policy, and also we are impacted. In terms of model algorithm perturbation, we have robust statistics that's actually set me on the path of trying to integrate both data perturbation and algorithm perturbation together under stability. Semi-parametric, lasso and ridge regression, the two choices we often struggle with, which one do you interpret? And for non-convex optimization like deep learning, each mode actually is a well-defined model. We basically search over many models, and often they give similar prediction results. But for interpretation, that's the frontier, right? We know we cannot interpret each individual weights. We have to find something interpretable. And for a neuroscience project, I don't have time to discuss here, we call deep tune. We have to confront with 18 different models based on deep learning and regression, give similar prediction performance, and which one you interpret. And we end up using stability principle again at the gradient level, try to maximize the fitted model, kind of borrowing idea from deep dream, we call deep tune for neuroscience. And you have different kernels, you have sensitivity analysis in Bayesian modeling. So all of these are there. But one thing we don't talk about, and this is our outstanding co-chairs for the meeting, if I ask them to solve a problem, will they take the same approach? There's this researcher to researcher perturbation, and team to team perturbation. Even your version yourself 10 years ago probably do something different than today. Which one do you use? And the climate scientists are already there. Often you see plots like that for average global temperature change. They're from 9 different teams and different models, and they plot them together. So they already, I was called doing PCS inference to have these perturbation intervals, which is taking into account the different user initial condition, different processing of the data possibly, and similar, hopefully, PDEs to drive these climate models. So there's something always bothered me when I was even a young faculty. I knew my colleague would do something very different from me. And will we reach the same conclusion? So we make all these judgment calls, some because of education, some because time constraints, some just because we did that. So all of this, I think, is best recorded. If you say that you use lasso because it just felt right, that's evidence. Or you thought hard, said your problem actually have sparsity. Say after Gabor transform, a lot of the V1 neurons actually are sparse because it's local to a particular location. And that's something else, right, for me to judge your result. So all of that is very hard to express in mathematical symbols. So we need documentation and detailed recording on why you made judgment call. Just be very honest. Sometimes we just do what we did just because we didn't have time to think too hard. Write that. That's very informative for me how to take your result. So the documentation really tried to bridge reality and models. So here's reality. Genomics, that's the world I live in. And here are models. Models are mental constructs. They have nothing to do with each other unless you build a bridge. Is there a bridge? Do you see a bridge? Maybe, maybe not. It's under the fog. So you have to do the work and give quantitative and qualitative narratives so that your probabilistic models or machine learning models have reality correspondences. Because the program is always going to run on your data, and you start interpreting. Some is good, some just illusion. You create the illusion from the model, you have to show evidence that actually captures reality. And you document your judgment calls. Otherwise, we might be on a very grounded foundation. And people ask me, how do you choose perturbations, right? It's infinite. I agree. You can just do all possible ones, so you have to stop at some point. But if you pledge to the stability principle, then you don't want to try everything, even have the energy and computing resources, because you probably end up with nothing if you say, I'm only going to interpret parts that consistent over these different versions of my process. So that will force you to think carefully, why are legitimate perturbations? So for genomics, as I'll show you, we didn't do linear models. I was explaining why. We did random forest because the decision tree have some biological support, something called thresholding behavior at the molecular level. So I think more and more we have all these choices to make. We have to pay more attention to what we call the matching of the analytical fibers of your argument to the domain knowledge, which in science probably is a little easier to come by than a new field. And you document the appropriateness. And this way, you have a well-documented process. Then you can go back and maybe change if you want to. So to really integrate machine learning with statistics, we also went into expanded version of statistical inference. So statistics, if you go back to 100 years ago, Fisher time, really try to do conformity, really try to make decisions for scientists. I think now we have to retreat from that very bold position to really just we're providing one source of evidence instead of look at the p-value. If something, there's science. I personally don't think we have that evidence to do that, but we're still very useful. So you want your process to be transparent, and you can report the strength of the evidence than just p-value large or small. But p-value have created a lot of problems, and psychology journals have banned it, actually. But it's not really p-value's fault. As U.R. Benjamini said, you should complement it with confidence intervals, but also the effect size. One problem about p-value is that if the model is wrong when you have large sample size and you don't take into account dependence, you're going to reject all non-hypotheses mostly, because everything becomes so magnified under the sample size that everything seems important, but actually your model is wrong, not because your hypothesis under the model is wrong. And normal approximation is also a problem when you go to such a small, far on the tail. You don't have the precision to do approximation there. I have been teaching statistics and probability in Berkeley for decades. It's only recently I started, after getting into causal inference, to start wonder about the foundation of probabilistic statements. So I definitely done for decades that the first class I would go out, write a big X, and that's a random variable. I didn't blink. But actually, even writing the big X is an assumption. Why is that? If you have fixed amount of data, and you don't care about anything else, any future data, you don't need probability distribution, just that data. If you try to imagine this data you have, it's a realization of a random process, you need to have another situation that can also generate another realization of the same process, at least two. Otherwise, why do you need a probability distribution? You should just work with your data, whatever. So that's really assuming that you have a stability that two data collected, either imagined or something, can be looked at as two realizations of the same random variable. And that's a healthy process to go through to say, what's that process? Why is that the future? And you will think, well, the future probably will be different. You go to transfer learning. You won't have exactly the same distribution. So going through that process is very healthy for data scientists. But if you don't have that assumption, you cannot even think of another process, then what does the p-value mean? Because you have to think about the sample space, what could have happened more extreme, and you cannot even think about a second, forget about other situations. And then the p-value formulation is problematic. And p-value often measure model bias. It's not about the size of under your model, because you're making assumption if you do hypothesis testing, your model is more or less correct, and then you can test the size. And I don't know how about this community, at least traditional statistical tend to call true model, which I really don't like, because true model is not true. So I think it's better to use approximate and postulated models to be more accurate, describe what we do. It's better for beginners. And we should also do inference, like all the applied mathematicians now in data science. They also do inference. They do PDE models. We need to have a way to also bring that in together, either through synthetic data or directly through perturbation intervals. The climate models I mentioned, the 9 of them, they integrate data with PDE models. So the proposed PCS inference we're still developing, and that's why I call basic. You really think about the multiplicity of translation of a particular problem. Is this gene important for this disease? Through multiple algorithms or models. You need to take that into account so you don't reach different conclusions because you choose a different algorithm. And then you use prediction as a reality check, as a screening, before you do hypothesis testing. I think one thing really propelled the machine learning community was really the use of cross-validation. Even it has its faults, but it's still a reality check. And modern statistics, we used to have diagnosis, but now we moved away because high dimension is hard to do. So we need to bring back prediction better. It's a proper test, or at least cross-validation. After you pass that, you think you have decent prediction, then you can think about these testing problems. And then you take into account both problem formulation and data cleaning together have these perturbation intervals, which are a lot bigger often than just forget about data cleaning and just do one way and have the probability model thrown at the clean data and then have a p-value or confidence interval out. Then you summarize and write it in a humanly understandable form. So one very important problem in a lot of the problems is the importance of features. So we did a simulation here just to compare PCS-driven method and with some post-selection inference. To be clear, post-selection inference, they try to control FDR, false discovery rate. But what's surprising, we do pretty well. This is one is under the so-ideal model, the other misspecified models. This is the ROC curve, so you can see that the higher close to 0, 1, the better. But to our surprise is that if you didn't do the post-selection correction, you just pretend you didn't do lasso and just do asymptotic normal approximation, for feature importance, it works not badly. So it just says that depends on the metric, you might want to use different methods. It's not like post-selection is always needed, and also computationally it's more expensive. So back to the 9 climate models. So if I take from the 9 models, we're going to say that at 2090, we're going to have average global temperature increase probably between 1.5 to 5.5. And this is a lot more informative. We know that the recent data definitely is not saying we are at the low end. Right? This really gives you a legitimate reporting for perturbation intervals, and which is informative for the public and for the scientists. So the next topic I want to talk pretty quickly is really adding more stability to random forest. I think this audience really understands random forest, so I will go pretty quickly. So start with the work with Ben Brown, who is a co-lead, and Basu now a postdoc, was a postdoc, now at Cornell and Columbier, former student, now at UCSF. So we really try to do pattern discovery. We're not trying to do pattern recognition because we don't know what that patterns are important. And we're looking for interaction. The polynomial traditional statistical interaction do not work. It's exponential or combinatorial increase complexity, but also many of the genes don't have important main effects. So you cannot just look for main effect first. So we work with a lab, through Seneca's lab on Drosophila, and we know that there's this important discovery about Eve stripe, about the segmentation of Drosophila or fruit fly. 4 genes interact. So what we try to do, turn random forest, which does really well predictively, and then give interpretation. And the reason we like decision trees is because there's something called the French flag model in development biology, saying biomolecules have to have plenty before they interact. So it's a thresholding behavior, which is captured by decision trees. So random forest, we all know, we add more stability because random forests already have data and algorithm perturbation, right? You perturb the data, you also randomly select the features so that result in model perturbation. So we do self-dimensionality reduction, use importance index, and we use something called random intersection trees to find intersection very fast, and we have an after loop of calculating stability scores. So the first step, random forest, and we use, say, important index from random forest. And we have work we call MDI-OOP by Xiao Li and Hugh Wang will be on Wednesday, so we have a new way of removing some of the noise in the indexing. And then you reweigh. So you now downsample the less important ones to the second iteration. And then we use something from the market basket research, try to find intersections of the red people, what they bought together, what the blue people bought together. So this in random intersection trees by Shar and Manhausen, it's very kind of spiritually like stochastic gradient descent in the sense that it takes one observation at a time, and it's greedy. You take another from the red group, and you just, if you have sparse intersections, you quickly go to the end. So that's how we find intersections. And we turn our problem into the market basket problem. Each path becomes a 0, 1. If a gene gets split, we call 1, otherwise 0. And then we can just do random intersection trees, and we have an after loop, and we collect the fitted, the common ones with a score. So this is an enhancer Drosophila prediction problem. We try to predict which segment of DNA is enhancer, which is a transcription factor switch to start transcription. And you look at the left, it's the ROC curve, the 3 iterations. We don't lose, for this problem, any predictive accuracy. This is on test data. But you look at the right, on the x-axis, you have the stability scores. On the y, you have the names of the biomolecules. The red are pairwise interactions, and the blue are the 3-way interactions. So the technology is beginning. You can do 3-way interaction physical experiments. So we become a recommendation system. If you look at the pairwise interactions, we just cut it 0.5, pretty common sense. Actually, 80% of pairwise interaction actually already validated in the literature. So this was after we already submitted the paper. We talked to the biologists and they were happy, but we didn't dig into the literature until the first version was submitted. For the 3-way interactions, these 3 important genes called Zelda, Giant, and Kruppel, then we basically have a recommendation for the lab to do experiment to see whether when all 3 are high, they are drivers of enhancer status. So the iterative random forest is really our contribution, Ben and I, to a new project with Chang Zuckerberg BioHub on vascular health and prevention. So we try to find gene drivers for heart defects and plan to do single-cell experiment. This is in collaboration with cardiology from UCSF and Stanford. So the last bit is about interpreting, right? So I said I really went down the PCS route through interpretation, and we end up interpreting the iterative random forest result for human consumption, for decisions on human experiments. And there are other examples where we need interpretation. And if you have good interpretation, it can help build trust. And EU has GDPR really asks people, the algorithm, to have explanation. So some work, which went before us, was the 2016 that was written Zach's paper, and also Dash, Wallace, and Kim with very similar spirits, but we took a different path. And there's now a book also on interval machine learning, which really teaches students the different interpretation methods. And Lipton paper really made a nice connection to fairness and other concepts, and the Dash and Wallace and Kim paper really kind of it's more to the community people design interpretation method, what are the good evaluation metrics. Our approach is a bit for the people outside and saying that if you want to choose an interpretation method, what are the considerations that's the radar you should consider and compare. So it's like emphasis a little different, but very related. So we define interval machine learning as extracting relevant knowledge from a machine learning model. We try not to define interpretability. That's too big and philosophical. Concerning relationship, either contain data or learned by the model. We view knowledge as being relevant if you provide insight for a particular audience to a chosen problem. And the goal is for communication, action, and discovery. So we have predictability for reality check. We have descriptive accuracy to see whether the method will objectively capture the relationship. We have post hoc and model-based already in the literature, and we emphasize relevance to a particular audience and to a particular problem. And sometimes you have to trade off descriptive accuracy. For each random forest, for that Drosophila problem, we didn't have to. We kept the predictive accuracy, and we got the descriptive accuracy out through extra stability. So model-based interpretability, people are like, well, I want linear, but actually you can only have a few terms. You have 100 linear terms, you're still not interpretable. Same with decision trees. You can simulate. That means you can go through the decision process as the algorithm, but if you have 10 splits, more than that, you're going to have a hard time to remember. Even deep learning is not most interpretable, but the modularity really helps. And also, you want domain-driven feature engineering and model-driven, and later model-driven can become domain-driven as well. And post-hoc interpretability, we follow the literature. You have global, and you also have a local. And global, you can have scores, significance, and through visualization. And the paper contains actually the way we try to explain interpretability is actually through many examples from our own work and other people's work to demonstrate the concepts. So the last bit, I think I'm kind of running out of time. 5 minutes, great. Is this generic algorithm we developed for deep learning. So it's really a series of Arclair papers. Try to give importance not just for a single word or single pixel, but give a collection of them so you can see interactions. And the last one is really try to use that to improve the model. So you want to suppress certain feature, you shouldn't use that. Can you use that in the fitting process to suppress that? So there are two broad range class of interpretation methods. One is like gradient-based, the other occlusion-based. You remove the certain parts and see how metric changes. And the paper started from when Jimmy did an intern with Peter Liu in Google Brain, and I joined later. So for this first paper, we just look at LSTM and collected the different relevant terms for different words and phrases in a computation efficient way and have the scores. And the second paper, we built it generalized to other deep learning models and also have a nice visualization. So here's an illustration. So this is a sentiment analysis problem. And this sentence was eventually labeled wrong as positive. It should be negative. And you can see the score colored. Blue means positive. It's really, when the negation happened, the orange, that was right. But then the last step, it didn't get kept. So you identify when the prediction got wrong. Similarly, for this PUG prediction, you can label the different regions. This is, we just add one at a time, use the amalgamated scores. And you can see the skates are very important for PUG prediction. Even you remove the PUG from here, you're going to predict PUG. So this just review correlations in your model, which some of them you might want to debias. We did 2 human experiments. One's about good and bad. So we changed models, make something good. Take a good model and randomize ways, keep the prediction the same way, but make it not so good and see whether human can tell. And the other is really just based on the interpretation and ask the humans. It's a relatively small experiment, like 11 people, whether they can trust. So together really give some promising result for our method because it really comes ahead for the data sets we consider. And the last bit in submission, we actually used ACD to try to improve the explainer model or surprise certain things we don't want to appear in the model. Just the last couple of weeks, we start teaming up with 2 people from the Berkeley Center for Cosmology, cosmology physics, Francoise and Vanessa, and led by Woo-Suk and Chandon, and joined by Faku from my group. they try to simulate, cosmology is part of astronomy, you try to simulate the universe from the beginning. There's a very important parameter called omega m, which is really measuring of the fraction of space that is occupied by mass. And if they forward simulate the model, get the map of mass in the universe, the purple one, which you observe. So this is on simulation day before we use the real data. And CNN actually predicts really well the inverse problem, from the purple image back to the cosmological parameter, omega m. But what does it learn? CD can be generalized to really give importance. So the interpretation is not in the pixel space, it's in the frequency space. So the CD methodology allows us to translate the band in the Fourier domain to the image domain and get a score. You can see that the different bands, a peak at the 0.3. That means that's a very important band for the inversion of the problem. And the goals of the interpretation for this project are quite general. There, we want to save on computation because it takes a lot of computing power to simulate. And we want to understand which feature drive the prediction, general, and we also want to give trust to using deep learning, and also distill the deep learning model into something simple. Preferably, in this case, you want to go back to generative and mechanistic models. So I have gone through a full circle that the success of this goal serves as a validation of interpretation method, and really I want to have a data science process, one culture, instead of two cultures. So to finish, we have PCS and PDR, both work towards veridical data science. And I hope you find both useful for your projects. And domain knowledge is extremely important, as both the Drosophila and the cosmology project. And the next step, we have many projects in my group try to make it PCS compliant. That means we actually follow the steps. And we unpack PCS for different domain experts. And we try to do some theory and speed up stability calculation and build a platform. And working on a book. And we have similar steps for PDR. And here's a plug for a workshop we are organizing at Simon's Institute called Interval Machine Learning in Natural and Social Sciences next June. And it's part of the summer cluster with my co-organizers listed. One last thing I will mention is that people actually at the center of our enterprise. And people make things truthful or not truthful. So I'd like to thank my group who really follow, we do quality research, often very slow. And I think the challenges is that we need people work on multiple methods instead of I'm deep learning person, I'll use everything, all the problems are solved by deep learning. Sometimes a good idea, sometimes I don't think so. So we need to understand different methods. We need more precision and vision papers. And AI actually have a hidden elephant or big elephant in the room is that the computers takes huge amount of energy. And do we want to consider that when we design algorithms? We need a few common, robust, or a lot of this deep learning-driven software really useful, but it's not completely robust and reliable yet for critical applications. And I sometimes have nightmare about my own algorithm one day will be used by a doctor to treat me and kill me, right? We don't have any certification and treat our kids. It's just out there, it's good about open source. We need to start having certification and labels so people to use our software better. And we should do red tagging, not just in software development, but also in development of machine learning algorithms. And that's one thing I talked to the organizer. I think we need to have trustworthy publications. Personally, I have a hard time keeping up with the publication. And if we just keep publishing, we have more papers to read free, we have less and less time. So everybody, there has to be a community effort, have to raise the bar a bit higher when we push paper out. There's no other way to solve this problem. I want to build on other people's work because problems are very complex. But I often have a hard time. A lot of interesting idea, but it's not complete. I don't trust to build my work on top of it. So I think we really need to it cannot work if we only have one person doing this. So we need to have the community agree. And my argument is that for top young people, this is not a good approach for you. I think your neurons work very differently. You write okay, good papers, then you push yourself and challenge yourself. So you're going to, your intellectual potential will suffer as a result. You keep pushing paper on instead of pushing for your full potential. And we need a fair collaborative environment. Yes, this talk really addressed a lot of the issues there. And we also need team brain. So here are the papers. And we have upcoming book for upper division and beginning graduate student and other people try to come in. Thank you. Questions? Yeah.
Yeah, we have time for questions. If you'd like to ask questions, there are microphones to the left and right, my left and right, your right and left.
Question?
Yes,
in a
great.
past life as a researcher in wind energy, I ran a study that was basically analyzed the analyst, which was very much looking at this perturbations introduced by the person doing the analysis. And what I found was that there was significant differentiation, but every company was completely unwilling to be transparent about what their methods were, just because they considered it to be industry secret. So I'm wondering if you have any perspective on how we can deal with these analyst perturbations where industry secrecy is a priority as well.
I think some encouragement or pressure from the community could help. For example, if this conference, NeurIPS, going to say that I'm going to start those papers who have gone through this, have transparent documentation, and ask the reviewers to look for such papers, that will be encouragement for some companies, some research to move this way. It will be a slow process. But I think if we start, in 10 years, we'll be in a better place, especially when AI enters every corner of our life. So I think it's going to be a very slow process, but conferences can really help in terms of instruction to reviewers and ask documentation on GitHub. The fact that if all the details, say submissions to NeurIPS, are required to be put on GitHub, it just automatically, when people put things out there, they're more vigilant. Even we only do a random sample and to take a look. So that's one idea that might work.
Hello, thank you for the talk. So I wanted to ask, because you put a great emphasis on stability and trusting the networks that we train, I was wondering, so in recent years, a lot of the papers that have been published typically did not put much effort into training on a lot of different random seeds for initialization.
Yeah.
And so my question was, are you aware of any research that looked into how much the results of training deep neural networks can actually spread just by random initialization? I'm aware of one publication from Erhan et al., but it's kind of dated. They looked at 2-layer or 4-layer MLPs, but for like the current state-of-the-art networks, I'm not aware of any. So can you speak to this?
Well, actually, I'm not aware either. I think that would be a good thing. That's about if you have like the deep learning and all these links to these papers, I think will be very helpful to users. So we use these random seeds most exciting in a positive way in some non-negative matrix factorization for genomics. We actually ask, when we select the number of components, to ask these different random seeds to get the most similar result. And that actually gives us a very biological, meaningful result. So that's more positive than what you're discussing. I think it would be very interesting if there's an effort, people kind of even just collect, like maybe there's a link on all these papers on stability. I think would be really helpful. Right now, I talk to people, actually many good groups already doing stability, but the paper is still written in a different way. So there's some standardization in our attempt to call PCS. Definitely it's unify many things people do already.
Thank you.
Thank you.
So I think we have things relatively easy in machine learning in terms of trying to look at these perturbations. But in the natural sciences, it costs a lot of money to say, use 3 different chips to image genomic data or something like that. Do you have any thoughts on how society can kind of arrange funding in order to pay for something like that? Particularly given that whoever publishes first is going to get credit, even if you had like 3 replications.
I think the funding agencies could encourage more. They can have some designated grant just for replication. I understand that you cannot have every grant only for replication, but there should be some funding going for replicated results, especially for the important one really impacting, say, a major cancer treatment. It's going to go to clinical trial, involve thousands of people. Things like that, I think, needs some replication. Yeah. But we cannot afford really for everything. But that austerity kind of economic paper, I wish there was a replication before the countries already follow that policy.
Thank you.
Yeah.
So in the interest of time, we'll take one more question from over here, and then everyone else can ask offline.
Yeah, I'll be happy to answer if you come up. Yeah.
Yeah, thank you for the nice talk. I'm expanding on a previous question that was asked before regarding how much should we trust the network, given that there are a lot of things that can change the predictions and the feature importance of the network. For example, the random initialization, the hyperparameters that are used to train the network, the data split, and the attribution method that was used to get these feature importance, for example. I'm wondering if you can comment on the challenge of the problem itself.
I mean, definitely going to consume more energy if we do all these different perturbations, but it's a trade-off, right? So if you have treatment in doctor's hands, the risk is human's life, right? So, but I think if we work as a team, that's why I think concentrating on fewer methods than everybody does their own method. I understand really well. I think that's a way to kind of shortcut a bit. Say, if everybody loves deep learning, right, we should have really understand deep learning much better or random forest. So a few friend runners, we can have more community efforts to maybe organize a collection of papers and to really say the pros and cons and in one place so other people can build on top of each other. So that comes back to trustworthy publication. If we have really quality publication, it's much easier to solve this problem because we can build on top of each other. But we're also working on trying to use random seeds, maybe coupled, to save on the computation instead of doing random seeds. So that's also another area we might get some gain.
Okay, let's thank Ben again.
Thank you. Thank you.